Hello and welcome to the 24th lecture of this short course called Behavioral Theory of Systems with a View Towards Data Driven Control. So far we have been doing mostly behavioral theory. Now we will start the second part, the subtitle of this course, that is data driven control. We will start with first the idea of identification. So this idea of identification that we will be seeing here in this course will be a little different from the conventional idea of system identification, where mostly it is done from a state space point of view. But here we will use this idea of behavioral theory that we have developed so far, in order to do system identification using those ideas. And we will see that mostly just simple ideas from linear algebra will take us quite far as this identification and other data driven control questions are concerned. Okay. So, a very important point to make that at this point we should make is that so far we have mostly looked into continuous systems, right, and I kept on saying that similar ideas hold for discrete systems. I will give you exercise problems which will tell you how to get those equivalent results in discrete systems as well. For the data driven control and identification part, we will mostly be considering discrete systems, and in that we will consider two distinct cases of discrete systems, namely when the indexing set, remember the idea of indexing set. So, the indexing set T sometimes will be Z plus, by which we mean these numbers 0, 1, 2, 3 dot dot dot, or sometimes it will be just Z, by which we mean 0, 1, 2, minus 1, minus 2, right. So, these two cases will be discussed. It is important for us to note that for these two situations the two operator rings are different. So, for example, when we have T to be equal to Z plus, in that situation we have sigma operator, which is such that when sigma acts on a trajectory W, this evaluated at T is W at T plus 1. Okay. Right. So, in this case you see if the trajectories are just this, then so okay, let me not draw this, it is not required. So, when sigma acts on a W and the value of this guy at 0 is equal to W at 1, right. So, because the trajectories are described like this, in this case it may not make sense to invert this sigma inverse, this sigma. This may not be a valid operator to talk about for all trajectories. I will tell you what the reason is. So, you see, for example, whenever there is an operator P sigma, P sigma W is equal to 0 is a kernel representation, right. So, this is the behavior here is all those W's for which P sigma W is equal to 0. What is this W? W is going to be a mapping from T to R, in this case scalar. So, this is R. So, that means for this particular case you have Z plus 2 R. So, that means W is like, I know W at 0, I know W at 1, W at 2 and so on. So, these are the various values that W takes at various points on the index set, is on the timeline, right. So, this is just like the way we have been representing behavior. This is kernel of this operator P sigma. Now, notice if sigma were invertible, then what would happen? For any P sigma, if it is invertible, if the inverse is also a legitimate operator, then see what happens. P sigma w is equal to 0. I multiply by P inverse. So, whenever P sigma w is 0, P inverse sigma P sigma w must also be 0, but that is equal to just 1. So, that means w is equal to 0. So, no wonder that if an operator is invertible, P sigma invertible implies that kernel of P sigma is equal to 0. Okay? Now, notice that if we now have our T to be just Z plus, and on that if I define sigma acting on W equal to 0 for all T in Z plus, what does this mean? This means sigma W evaluated at T must be equal to 0 for all T in Z plus, but sigma W T is W at T plus 1 is equal to 0 for all T in Z plus, which then implies that W at 1 is equal to 0, W at 2 is equal to 0, and it continues like that. But it does not say anything about W 0. W 0 can still be any number. So, the trajectories are alpha, that is a legitimate trajectory in the kernel of sigma, and this is a non-zero trajectory, right. If it is a non-zero trajectory which is inside the kernel of sigma, then this implies sigma cannot be invertible. So, sigma inverse does not exist. Now, compare this situation with the case when we have T equal to all of Z, and there now if we once again write down the same equation, that sigma W is equal to 0, that would imply W at T plus 1 is equal to 0 for all T. Now, in Z, you see, if it is in Z, if T is allowed to be anything from Z, then everything, this is the same as saying T W T is equal to 0 for all T in Z. Just think about it. If W T plus 1 is 0 for all T in Z, W T must also be 0 for all T in Z, which means W is the 0 trajectory. So, indeed sigma W, kernel of sigma is 0, kernel of sigma is indeed the 0 trajectory only. So, therefore, sigma is invertible. So, that is why, so sigma inverse exists in this polynomial ring, in this operator ring, in the operator ring. All right. So, in this situation, what does this mean? This means that whenever we have T to be equal to Z plus, then the corresponding operator ring would be R sigma, that is all polynomials in sigma, the shift operator sigma, the left shift operator sigma. On the other hand, if T is all of Z, then the corresponding operator space will be R sigma sigma inverse, right. So, like before, we will be denoting this by R xi, and we will be denoting this by R xi inverse. Okay. Okay. So, with this in place, let us recall where we were, right. So, yeah. So, we will be discussing mostly in fact exclusively discrete systems, discrete trajectories when we are talking about system identification and data driven control from today onward, from this lecture onwards. Okay. So, now so I think it would be best to take this abstract idea of identification first, and then we will see how this abstract idea applies to the situation of identifying dynamical systems given some data about the dynamical system. So, here is the abstract approach, and it deals with the idea of most powerful unfalsified model. Abstract idea of identification okay. So, bear with me for a while. If you don't understand something, then just go back to what I am saying, just do a rewind and replay what we have been discussing, because the idea is going to be a little abstract. So, like before, what we have is a universum, a collection of all possible outcomes of a certain phenomenon, that is our universum like before. Okay. Now, inside this universum what we will have is a data set, which is going to be a subset of all possible outcomes. This is a data set. Yeah. Now, there will be a model class and this model class is what? So, this model class contains these guys. Does it look familiar? Of course, they are behaviors, right. These are, so each behavior is a model. Every element of a model class is called a model. In this case, it is just a behavior. What we mean by this? This is a subset of the universum, but this has some special properties that we want from a model. For example, we may ask the question that we may say that these models are all linear time invariant dynamical systems, linear time invariant dynamical systems which are given by ordinary differential equations with constant coefficients. These are the properties that we impose on these models, and when we collect these all possible such models, we call it the model class, right. Now, given a data set, we say that a model or a behavior from our decided model class explains the data if the data is contained in the behavior. Very simple. I say that, so the behavior is essentially maybe a collection of laws, right, maybe a dynamical system. When I say that the dynamical system explains the phenomenon that has been observed through the data, through the measured data, it essentially means that the trajectories that are allowed in the behavior, among those trajectories the given data set trajectories are also there. So, that is why B explains the data. Okay. Now, in that sense we also say that this model, so this is equivalent to the idea of saying that this model, listen very carefully, is unfalsified by the data. Unfalsified by the data. Is that okay? So, what would we call it unfalsified? Well, you see, when some phenomenon is there, you observe something, right? You observe something and then you propose your theory to explain the observation. How to explain this? Like like astronomers long back observed that this is the motion, this is the planetary motion, this is okay. Well, Mercury, sorry, Mars travels around. Okay, Mars moves like this. Yeah, astronomers have observed, and then on that, Kepler gave his famous Kepler's laws, the ones that we discussed at the beginning of this course, right? And Kepler's laws then explains the movement of this of Mars, right? Is this the only possible law that explains this data? Not really. You could have given a different set of laws or different set of equations which might also be such that it explains the data. So, there is no way that a given model is the only one that explains the phenomenon. There could be multiple such models. But if you propose something which is like preposterous, you propose something, you say that okay, no, Mars shows this kind of a movement because Mars is moving around the Earth, yeah, like Earth centric model, the ones that were proposed long back, yeah, before the heliocentric model or the sun centric model came up. So, you said okay, no, this is the Mars moves around Earth, Earth is the center of everything. That clearly is falsified by the data, because if that were true, the kind of trajectories that Mars would have made, the kind of movements that would have been observed for Mars, yeah, that movement does not match with what we see, right. So, therefore, that model, the Earth centric model, is falsified by the data that we have about Mars's movement. Yeah. So, you understand the idea of falsification when. So, any model worth considering must certainly be unfalsified. If it is falsified by the data, then you should just throw away that model and consider move to a different model. Now, here comes another important observation. Among all unfalsified models, there could be several models which which are unfalsified by the same data. Suppose I have B1, yeah, in the model class. I also have B2 in the model class, and they are such that both B1 and B2 are unfalsified by the data. So, that means both B1 and B2 are such that D is contained in B1, and D is also contained in B2. Both of them are unfalsified by the data. Okay. Now, in that situation, we say the following. We say that B1 is more powerful than B2, and we denote it by B1 is more powerful than B2 if, notice carefully, B1 is contained in B2. You may ask, this may seem a little counterintuitive, that why are we calling this more powerful when this certainly is a smaller set. But you see here a smaller set is actually better, because smaller set means you are putting more restrictions, right. You are going even closer to the data. So, when you have the data D and you have some B that explains the data, so that B contains the data, right, then you may sort of have too many extra things within the behavior, right, within the model. The model may be like too big and it still explains the data. If there is a smaller set, smaller behavior which still explains the data, that means it is better because it goes even closer to the data. Let me give you an example. So, suppose right. Suppose if it foresaw that the universum also is allowed to be a model, in that case every data is explained by the universum, no, by definition, because the model because the data is measurement of the phenomenon and all possible outcomes of the phenomenon is the universum. So, obviously, D is a part of D is contained in the universum. So, this is a model, yeah, which explains everything, yeah. So, it is almost like saying that everything that is happening around the world, all of take the sum of all of them, then every single phenomenon will be a part of that. But is that a good model? Of course not. It is like too big. It's too huge to handle. Yeah, this is not a good model. A good model is the one that does the bare minimum to explain the data. Yeah, it explains the data and does only little bit more than that. Yeah, to stay within the model class. Okay. So, that is why a model whose behavior is smaller is a more powerful model. Okay. So, in that case there is an obvious definition of a most powerful unfalsified model. Yeah, or MPUM. What does that mean? An MPUM is a model within the model class that is unfalsified. So, it explains the data, and finally, here is the point. This is bullet 1, this is bullet 2, bullet 3. If there is another model in the same model class which also explains the data, this would mean B is more powerful than B prime, which is equivalent to saying B would then be a subset of B prime. Obviously, if there is any other model unfalsified by the data, it had better be less powerful than the one that is claimed to be an MPUM. From this definition itself, it follows that MPUM is always unique if it exists. MPUM, if exists, must be unique. Yeah, because if there are two MPUMs, then one will be contained in the other, right. So, therefore, they should be equal. Yeah, so set wise, that if there are two sets and both are subsets of the other, then the two sets must be equal, right. So, therefore, MPUM must be unique if it exists, but we do not know yet whether it exists or not. Let us get some examples of situations where MPUM indeed exists. Yeah, but make no mistake that there could be situations where MPUM may not even exist. Luckily for our case, the kind of systems that we will be looking at, dynamical systems and dynamical systems and trajectories and all. So, for that situation, it so happens that if you insist on dynamical systems are linear shift invariant and they have they are coming from solutions of ordinary difference equations with constant coefficients, then it so happens that MPUM always exists, and therefore, they exist uniquely as well. Now, here is an example of an MPUM. Okay, right. So, I am tempted to give a philosophical example, but I think I should refrain myself from doing that. Let me give you anyway a linear algebraic example, which will be easier for us to understand. So, suppose our universum is our universum is this Euclidean vector space of dimension r, dimension n over the real numbers. Okay, that is the universum. What is the model class? Suppose the model class is the collection of all linear subspaces of R n. Okay. Notice that when I say model class is a collection of models which themselves are subsets of U, correct. So, it then automatically follows that model class must itself be a subset of the so called power set of the universum. What is the power set? Power set is the collection of all subsets of a given set. Look at U, consider all possible subsets of U and collect them, that is the power set of U. Why is it called power set? Because if it is a finite set, then the cardinality of this power set is 2 to the power the cardinality of the set in the argument, yeah, that is why it is called the power set. But in any case, the power set is the collection of all subsets. Now, the model class, each of them, so a model class, every entry in the model class, every element in the model class is a subset, right. So, therefore, it must be a subset of the power set of U. So, each element of the model class is a subset of the universum. So, therefore, this collection of models is a subset of the power set. Okay. So, here also you see that given R n, you look at all possible subsets of R n, that is the power set. In that you put this extra restriction there that these subsets cannot be arbitrary subsets, they must be subspaces, which means they are closed under addition and closed under scalar multiplication from R. Yeah, those are linear subspaces. So, these linear subspaces are the ones that we are considering as our model class. Now, what is the data? Suppose the data is just a collection of vectors v1 dot 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 up to Vr, does not necessarily have to be finitely many, but let us assume for the time being that it is a finitely many. Okay. So, can you give me the MPUM for this? Think about this. If you have done linear algebra seriously, then you should be able to tell me what this what the MPUM of this is. The MPUM here is nothing but the span of these vectors. Why? Because that is a subspace, this span. Does it explain the data? Yes, it does contain D, because the span of vectors contains the individual vectors. Okay. Why is it most powerful? Because it is the smallest, smallest subspace that contains D. It is the smallest subspace that contains D. Why is this the smallest subspace? Do it as a part of your exercise. This is something that you must have surely done in your linear algebra course. Show that the span of V1 dot 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 Vr is in fact equal to the intersection of all subspaces S, that means S from the model class, such that S contains D. It is the intersection of all those subspaces, that is the span. This is a very standard exercise that is given in every linear algebra course. So, given a finite set of vectors, infinite set of vectors also, look at every subspace that contains those vectors, and then take the intersection of all those subspaces. what you get is also a subspace, and that subspace is the span of these vectors, right. So, therefore, this is the most powerful unfalsified model, because why? You see, every S in the model class that explains the data, yeah, is there in this its intersection is there. So, therefore, this must be contained in every S for all S in M such that S explains the data, yeah, because the intersection, it is contained in all of those guys, all of those these elements whose intersection is this set, right. So, therefore, every model that explains the data must also must be containing this particular subspace. So, this particular subspace is the most powerful one. Now, it so happens that you see, for the general case also, for the general situation also, there is a particular example. No? So, for the general case also, if it is possible, so okay, given the universum, yeah, and we have this data, right. The data also is coming from this set D, which is all possible data sets, and data set of course is a subset of the power set of the universum again, yeah, but that apart, there is an added information, nothing very important. But now suppose we have this universum, yeah, and suppose for all data in the possible data, all possible data sets. So, for every possible data, if there exists at least one model in the model class such that it is unfalsified by the data. So, we make this assumption first, assumption number 1, that for every data, yeah, every possible data, there is at least one model we know, yeah. Why is this a not a very restrictive assumption? Because this can be made sure by ensuring that universum is also a model. When universum is a model, then you always have a model that explains the data, that is guaranteed. So, this is not a very restrictive assumption. Second assumption is a bit restrictive. Second assumption is that suppose, now notice carefully, suppose for every M prime which is a sub model class of the model class, we have intersection of behaviors in the sub model class. If this itself is a model, if these two properties are there, then this implies that there exists a unique MPUM for all data in the set of all possible data sets. Okay. It is in fact logically trivial, it will just require us little bit of thinking to prove this, but we will do it in the next lecture, right. It will take some time which I do not have right now. So, we will do this in the next lecture, a very short proof, yeah, and then using this idea, this is a very simple but a powerful theorem, because this is what guarantees that that in the setting of dynamical systems, if you want to find out this MPUM, such an MPUM always exists if our model class is the class of all dynamical systems that are given by ordinary difference equations with constant coefficients, right, because it satisfies this intersection property. Okay. This and many more is what we are going to see in the next few lectures. Till then, take care of yourselves. Bye.